This is about the origins of language, the Pinker and Bloom paper and my paper. As a matter of fact, the talk that I'm going to give is going to be mainly on my part, so maybe I should start with some stuff on the Pinker and Bloom. There's more or less three things with Pinker and Bloom. Some of the things they say are dead obvious, and the reason they say this is all going to be boring is because it really is boring, because some of it is obvious. It's not the part that's cultural with language, the part that you pass on by learning and generations. That's not controversial. That's not even evolutionary. The only part that's evolutionary about language is how did it start and what's different between us and other creatures. And there's some aspects of language evolution that are not controversial, even evolutionarily. For example, to the extent that we have to agree on a code, we all have to share the code. He gave the example of parity, where you have handshake systems between different electronic communications, and you have to make sure that they're talking the same language, so to speak. That's also trivial. I mean, but that language isn't parity. Language isn't a way of agreeing on what kind of signal processing code we're going to use. Language is a way of talking to one another as we are now. And in that, there are two deep and controversial questions, not these trivial things which are easily settled, but what is language really, and what is the possessor of how does the possessor of a language or the master of a language differ from those that don't have it? And the other thing, of course, is the special case of grammar and universal grammar, which Pinker and Bloom completely avoid, even though, as you'll see next week, Pinker knows perfectly well what's at issue over here. It's because they avoided it. Well, I don't know if I should put this on the tape. Hang on a second. Well, I can't stop it. All right. How to put this?
You should figure out how to stop it so you can just say it.
No, I can't stop it except if I go to the... All right, you know what I'll do? I'll stop it here. And the readings that we're covering are Pinker and Bloom's and mine. So I have to talk about a little bit more about Pinker and Bloom. The part that that's uncontroversial, so that you take it home with you, is the cultural part, the parity part, the conventions, and stuff like vocabulary learning. Nothing could be more trivial than learning to attach a name to something. It's at the very least, it's paired associate learning, and then when you've got that something that's missing in language, which is what makes it language, then it's just associating a name with that. That's trivial. Agreeing on names is trivial. That's not what makes language special. Communication, non-linguistic communication, is trivial, but the part that Pinker and Bloom don't address at all, besides universal grammar, what I told you about already, and that we'll talk about next week, is propositionality, what it is that actually makes language different from other forms of communication. And that's all I want to say about Pinker and Bloom, because the rest of it is sort of unobjectionable but relatively uncontroversial stuff about the fact that, yes, language is a complicated thing, has lots of biological aspects. Speech is biological. You look, the evolution of the speech mechanism, that's all biological, and there was no controversy about that. The controversy was about language itself. What is language for? How did it start? What's different about those who have it and those who don't? You don't learn that from Pinker and Bloom. And universal grammar, that's a really special case. You don't learn anything about that from Pinker and Bloom. Okay, so now that's Pinker and Bloom. Now we're on to language evolution and my paper. I'm going to review the Turing test, Searle, symbol grounding, and Chinese dictionary obligatorily, because it's the same thing, but it becomes more salient as we move into language. The Turing test, as you all recall from the exam that you just took, is our attempt to capture our capacity to do everything that we can do. Do. The emphasis is on doing. And language is one of those things that we can do. We can do things with objects. We can manipulate objects, recognize objects, and then we can, yeah?
So does that, I'm sorry to keep going back to this, but does passing G3 mean something to understand?
I replied to you.
Yeah, and I didn't really understand.
Well, but this isn't really the right place to, okay. You can bring that up in your discussion part. All T3 means is passing T3, and T3 covers all of our doing capacity. Okay? Once you've modeled that, you've explained that. And language is part of our doing capacity. Moreover, and this is really important, language surely is grounded in our non-linguistic doing capacity. Searle's Chinese room argument showed that whatever it is that's going on inside your head, it can't be just computation. Okay, and it isn't. We're now talking about what to do in addition to, or what to do with computation in order to make it something more like language. He doesn't understand Chinese. Chinese is a language. Computation is also a language. It's a symbol system, but it's an ungrounded language. And mentally understanding Chinese requires grounding. But to answer John, it's not the same thing as grounding. Understanding Chinese is not the same thing as grounding. Understanding Chinese is grounding, T3 grounding, plus what it feels like to understand Chinese. So my version of the problem is the Chinese dictionary, and then I'm going to actually talk about a dictionary, the symbol grounding problem, which is what prevents an ordinary formal symbol system from being a language with a built-in semantics, and not just the semantics that you can project onto it if you read it on the page, is illustrated by the Chinese dictionary, because the Chinese dictionary is perfectly adequate for a Chinese speaker. They already have meanings in their head. So all they need to do is look at the squiggles and the squaggles, and they know what the meaning of the squiggle and the squaggle is. But for someone who doesn't know Chinese, it's no use to go up and look up a definition, and then look up, if there's words in the definition you don't know the meaning of, look those up and look those up. It just leads to an infinite regress. It doesn't lead to meaning. It just leads to more and more squiggling and squaggling. And the idea is to break out of that. That's the symbol grounding problem. And the suggestion is the T3 grounding the symbols in the objects that they stand for, the capacity, in the capacity to recognize and manipulate and identify and describe the objects that they stand for, is the way out of the Chinese room and out of the dictionary go round. And now I'm going to actually take an example. I'm going to take a real dictionary that we used a couple of special dictionaries, LDOC and Cambridge. One is Longman's and one is Cambridge, and we also use WordNet. The little ones are special because they were allegedly designed to define all of the words in the dictionary out of just a control vocabulary of 2,000 words. Allegedly, every word in the dictionary is just, they define it using just the 2,000 word control vocabulary. It turns out that they violate the, we had mathematicians working on this project, and the mathematicians can't stand this kind of messiness. They violate this so often. You have so many words that are defined with words that are not in the control vocabulary, and there are words in the control vocabulary that are undefined, that we decided that we had to actually start from scratch and actually generate a dictionary that would have been like this dictionary was allegedly designed to be. There were some problems with multiple meanings and the fact that we're treating a definition as just being an unordered string of words. When you say that a zebra is a horse with stripes, right, you're not just saying zebra, horse, stripes. And we're treating it as if all you're doing is saying horse, stripes. So that's a simplification. But it turns out you can do a lot. So treating definitions as just a string of words, and the word to be defined as just a string of words, you can do the following. This is a toy dictionary. It's not a real one. Don't take these definitions seriously. They were invented just to show you how we did this on a real dictionary. So here's a bunch of words. A fruit is fruit is an edible. Hang on now. A tomato is a red fruit. An apple is a red fruit. A banana is a yellow fruit. Color is, etc. These are not real definitions. They're just meant to give you all of the features of a little mini dictionary to which we apply our method, and then you can imagine how it would work with the real dictionary. So what we can do it here is, since tomato is defined as a red fruit, we can get rid of tomato, right? We already know we can get to tomato just from red and fruit. And we can get to apple, and we can get to banana. So we get rid of those. And then we've got these left. It turns out you can get to these by definition as well. You can get to fruit, yellow, and red. So we get rid of fruit, yellow, and red the same way. Anything where you already have a string of words that'll get you there, throw it away because the string of words is enough. And if the words in the string of words can also be gotten to by a string of words, throw that away as well. So we continue, we throw away edible, and then we're down. Now we can't remove any more words. Okay? This is the kernel of this toy dictionary. But this kernel is not. It is a small set of words, and when we did it in our real dictionaries, it turns out that it was about 10%. So you could reduce the entire dictionary to about a 10% kernel. But whereas it's true that those kernel words are words from which you can define all the other words, they're not the smallest number of words from which you can define all of the other words. That would be the minimal grounding set. Now for this dictionary, we can already say what the minimal grounding set is. So this is the kernel. We've got the kernel is the stuff in blue. And then that can be decomposed. The kernel can be decomposed even further into what's called strongly connected components. That means when the definitional arrow goes in both ways. You use A to define B. And that's circularity, but good is not bad and bad is not good in this toy dictionary. So that's strongly connected. And you can shrink it even further, and you get a thing called the core, which in this dictionary is really nothing. It's not and no. But in a regular dictionary, it's bigger than that. The core is not actually a minimal ground. We don't have a minimal grounding set yet. The core is simply something from which you can get to the rest of the kernel, and then you can get to the rest of the dictionary. What we don't have, actually maybe the core here is a minimal grounding set. In this toy dictionary, it is a minimal grounding set. What we don't have in the big dictionaries is the smallest number of words. That's a number, right? It's not particular words. The smallest number of words in the dictionary from which everything else can be defined. That would be a minimal grounding set, and its size would be the cardinality, or the size of the minimal grounding set. Yep.
Can you define tomato with those words?
No, please don't focus on the actual.
Pointing out that
Yes.
those words don't seem like they're adequate.
Yes, you can. I told you this is a toy dictionary, and they're not real definitions.
Right.
But if you do these procedures on a real dictionary where you have a real definition, the same thing will reduce. It just won't be these words. These are just toys. Okay,
Right.
These are not real definitions. You don't get a tomato is not fully defined by saying it's a red fruit. Okay, but definitions are like that. And in fact, if you're wondering about fully defined, no word is fully defined. It's like what I said about a picture is worth 1,000, 100,000, an infinite number of words, because there's always more in an object in a picture than any finite string of words that describes it. So what a definition has to be is enough to get you by. It can't be an and if tomorrow a day comes where our exhaustive our provisional definition of tomato is not good enough and is really getting confused, is this a tomato or isn't it? Then we have to enhance the definition further.
I was feeling okay with red fruit. I wasn't feeling okay with
Doesn't matter.
not
It's
red.
all just a toy. It's not real. It's not real definitions. It's just meant to illustrate the method. But the point that I was making was that not no is a core. It's a strongly connected core, which leads to the outside, and it's also a minimal grounding set for this toy dictionary, which is trivial. But when you take a real dictionary, yeah.
Sorry, can you explain how that core works? The not
This is a toy, and so I can't say anything. It means nothing, the not no. But in a real dictionary, if we could get it crunched down to the core, then from that, pardon me, not the core, but the minimal grounding set. The core and minimal grounding set are not the same. The core is a strongly, the technical side of this doesn't matter so much. I'm going to try to keep out enough details keep enough details out of it so you'll get the idea. Think of it as the fact that the kernel is definitely enough to get you to the rest of it. The kernel is unique. There's only one kernel in a dictionary, the thing that we've got there. But it's not the smallest number of words you can define everything else out of. Finding the kernel was easy. Finding the core is hard. In fact, it's NP complete, if you know that from computer science. So you have to use tricks in order to shrink it down to a core. And moreover, the minimal grounding set is going to turn out to be non-unique. There's going to be many different grounding sets of the same size. We think it's going to be around 500, but that's a guess. Around 500 words, but there are lots of different. Think of it as being like in a vector space, where you can generate all of the vectors in an n-dimensional vector space with n linearly independent vectors, n vectors that are not multiples of one another. But it doesn't have to be just the basis vectors 0, 0, 1, 1, 0, 0, and 0, 0, 1. It could be 2, 7, 4. Just as long as they're independent, you could use 3 linearly independent vectors to define, to generate all of the other points in a three-dimensional space. In the same way, you can define all of the words in English using different basis sets. And these are the minimal grounding sets that I'm talking about. We don't know what they are, and it doesn't matter for this discussion. It just matters that they exist, and that they're a lot less than the whole dictionary, and they're even less than a core. Okay, that's all you need for the present purposes. Because having done this, having found the core, and we can also build a kind of a hierarchy. How far away in definitional distance is a word from, say, the core? The ones in the core are at 0 level. The ones at the next one hop away or 1, and then 2, 3, 4. I think the furthest distance in this toy dictionary is 4. You have that. Now, you can do the same thing using the, never mind, anyway. Now, using that, I don't want to give you more details here than you actually need, because it'll just confuse you, and the concepts will come out clear with just as much as I'm giving you now. Now, I'm representing the circle there is the whole dictionary. The smaller ellipse is the kernel, and the smallest part is the core. If you look at, and the core, as you recall, is not the minimal grounding set, but it's that highly connected, it's like a big satellite inside the kernel. We did some correlations between whether you were in the kernel or in the rest of the dictionary, whether a word was in the kernel or the rest of the dictionary or in the core. And we found that depending on the, for some of these properties, imageability, concreteness, written frequency, spoken frequency, for written frequency, age of acquisition, and spoken frequency, there was a 0-1 correlation between whether you were in the kernel or in the rest of the dictionary. If you were in the kernel, if the word was in the kernel, it was learned at an earlier age, and it had a higher spoken frequency and a higher written frequency than if it was outside the kernel. And this is just the kernel. It's not the minimal grounding set. We could go further with imageability and concreteness, because there's a gradual stepwise correlation. It's not just an all or none in it or out of it, but depending on your distance in definitional space, the words get less and less imageable as you get further and further in definitional space, and less concrete. So it looks like somewhere in the middle there, something special is happening, and we're thinking that it's got to do with grounding. Okay? So, yeah.
Okay. Do you mind, because I think I understand it, do you mind just saying that?
Again.
Basically, what were you saying about the kernel, words in the kernel have a higher spoken frequency and lower age of acquisition?
So it has a lower age of acquisition, exactly. Lower age of acquisition, a higher spoken frequency, and a higher written frequency in the kernel. And the core is also, that's true of the core as well.
Wait,
the core is inside the kernel. That's even smaller.
Which one of those three?
The core is it's not, that's why I shouldn't have even.
No, sorry, okay, but in your 3 circles, which one's the
I have to stop this one. Don't worry about the rest. I'll review. You know the way Turing test comes back every week? The dictionary is going to come back, and this stuff's going to come back, so don't worry, okay? Now, if it's true that our vocabulary has a kind of a smaller number of words out of which everything else can be reached by definition alone, forget about everything else except that. But there's a small number of words out of which all the other words can be reached by definition alone. And those words are learned earlier, and they're more concrete, and they're more imageable, and they're more frequent written. Then the question is, how do we acquire those words? Because if we know how to acquire those words, then the rest of them we can get by definition alone, squiggles and squaggles, right? Because once you've grounded squiggles and squaggles, the rest are not squiggles and squaggles anymore. They're a combination of grounded words. That's really all you need, frankly. And probably that's all I should have told you about the dictionary stuff. Anyway. And so this is really a question about category learning. And this I told you in the categorization talk 2 weeks ago, and I'm going to repeat it so that it gets so that you get ready for your final exam when it's all going to be crystal clear. But what these experiments that we did on texture learning, which texture learning is just supposed to be a stand-in for any category learning. It doesn't have to be visual, it doesn't have to be auditory, but you need unfamiliar stuff that you don't know how to categorize, and then you need to learn to categorize it. And then when we test for categorical perception, you have to test whether something's changed in your perception so that before you knew how to categorize it, it looked one way. This is Whorf. And after you learned to categorize it, it looked a different way. And in these texture experiments, we showed that by teaching subjects to classify textures in two categories, telling them it was made by two different computer graphics artists, and you have to learn to recognize their styles. And we'll just give you examples. This is supervised learning. We'll give you examples, and you just tell us whether you think it was artist A or B, and then we'll tell you if you're right or wrong until you're getting it all right. And subjects, if you look in the middle, some subjects didn't get it. They didn't get better. And some subjects did and got to close to 100%. And all of them got to 100% with the easy ones. With the hard ones, some got it and some didn't. And if you looked at their, everybody got the easy ones. If you looked at their discrimination, remember that categorical perception has to demonstrate that there's categorical perception, you have to show two things. That the subject can categorize the stimuli alone, when given alone. This is an A, this is a B, this is an A, this is a B. And then when given different pairs of the stimuli, maybe two different A's or two different B's or an A and a B, and simply asked, are they the same or different? Or how similar are they? That's discrimination, right? So you have an absolute categorization test, and you have a relative discrimination test. And what categorical perception means is that after you learn the category, the discrimination changes. The discriminability of members of the same category goes down, they get compressed, and the discriminability of members in different categories gets enhanced, they get separated. That's the signature of categorical perception. And what we found was with the easy stimuli, there was no categorical perception. There was the kind of enrichment that you get with near exposure to stimuli, but everything got a little bit more separated. Everything was more, whether you were in the category or between categories, everything was a little bit more discriminable after. And that's probably because they were exposed to more instances, and it was already shown with unsupervised learning that if you're exposed to stuff over and over again, no categorization, you just see it, then they become more different from one another, just from exposure. But with the harder ones, where they really needed the training about what's what, we got learned categorical perception. The textures that were in the same texture category, done by the same artist, once they learned which ones were which, they became more discriminable when they were by different artists and less discriminable when they were by the same artist compared to before. Is that clear? That's learned categorical perception. And we did modeling of that, same sort of thing. This is a backpropagation neural network which has hidden units. The hidden units, we have, as a matter of fact, 3 hidden units here. So you put in shape as an input, and then it has to give you another shape or a response. It has to give you a response as an output. What we did was we first trained these neural nets, which had a shape going in, hidden units, and then an output. We first trained them to give us back the same shape in the output as we gave them on the input. That's called auto-association. And that's sort of the equivalent of mere exposure. All it does is enhance. It takes wherever the shapes are in hidden unit space, and I'll tell you what hidden unit space is in a minute, it pushes them a little bit further apart. Everything gets a little bit further apart from everything else. Hidden unit space means this. Again, we have 3 hidden units. In the beginning, their values are random. But if you present the shapes over and over again in auto-association, meaning you're training the units, that I want you're taking a 2-dimensional space, this is a shape, this is an L, with which we can have a longer upper bar or a longer lower bar, right? These are if you look at this, I can't use my pointer, but if you look at the shapes, you have an L with the upper bar varying and the lower bar varying, and you have various different combinations. And this is how we as gods classified them. There were 3 categories. But the first thing we did with our neural nets was not to teach them to categorize, but simply teach them to auto-associate. That was to get them up to speed with what the human subjects saw. Simply give me back the exact same shape that you saw. And if we train the hidden units so that they change their values, they change their activations using, don't trouble your heads about it, but the delta rule, which is the one the rule for changing weights depending on supervised learning. You get it right, everything trickles back and adjusts the weights. It adjusts the weights on the basis of the delta rule. You don't need to know it. Just there's some way that this net is learning to adjust its weights so that it gets the thing right. And getting auto-association right means giving me exactly the same shape that I put in. So remember analog, where this is mirror neuron stuff. I give them this shape, it has to give me back this shape. I give them this shape, it has to give me back that shape. That's all. Once we've trained them up on auto-association, that's the middle cube there. The cube is simply the 3 hidden units and what weights they gave to the 3 different categories. We have 3 categories here that were inputs. As you see, they're roughly separated, but they're not reliably separated in the cube. The next phase is to train that same neural net to categorize. It has to continue auto-associating, and in addition, it has to learn to call the 3 inputs on the left as call them one category, the 1, 2, 3, 4, 5, 6, 7, or whatever, 8 in the middle, the second category, and the 3 on the right, the third category. So first it learns to auto-associate, which is just unsupervised learning, and then it learns to categorize. That's supervised learning. And once it's learned to categorize, it's possible to put 2 planes into that hidden unit space that separate the 3 categories because they've now been, the hidden unit weights have migrated into different parts of this space so they can be separated by a category boundary, right? So in this neural net simulation, once you get categorization, you get something that sort of explains to you why it is that you get compression and separation. Think of it as being like hidden unit weights that are pushed apart in order to make it easier to tell the members of the categories apart. But of course, by squeezing things together, it makes them also harder to tell apart within their category. By making categories easier to tell apart from one another, by moving them away, you're also sort of compressing. You're separating and compressing, and that's what categorical perception does as well. What we did was we took these same neural nets and put them into little artificial creatures like Pac-Man that have to eat mushrooms in order to survive in an artificial world. And we had some mushrooms that were sort of like our grounding vocabulary that you had to learn directly by trial and error which ones were edible and which ones weren't. The Pac-Man had to learn. And you also had to learn which ones had to be marked. There were 2 things you had to do with mushrooms, and there were different features, different affordances for the 2 different categories, but the little creatures had to learn both the categories. And then there was a third category, the mushrooms that you had to return to, that you could learn now in 2 different ways. This is a toy world, just like the toy dictionary. I'm not saying this is the real thing. You could learn the third category the same way you learn the first and second category, which is by trial and error and reinforcement. But that's time-consuming, energy-consuming, risky, and it may not succeed. The alternative way was to learn it by hearsay, which is to overhear the others who already know it. And the only way hearsay works, hearsay wouldn't have worked for the bottom level categories because you didn't know what they were. But the reason that hearsay works at this third level is because the third category is just defined by the first 2. A returnable mushroom is a mushroom that has the features of an edible mushroom and a markable mushroom. So if you already know edible and markable, it's like knowing horses and stripes, you get zebra for free. And we put the creatures that could learn in this new way in competition with creatures that could only learn the old way. And within a few generations, there were none of the old way creatures. And we think that this is an indication of how the power of propositions, because this is a proposition, saying all x's are y and z is a proposition. It has a truth value. It's true that all x's are y and z. It's not true that all x's are y and not z, and so on. So we think this illustrates the power of getting new categories by instruction instead of induction. The degree to which it saves you time and risk. Yeah?
How is this different from combining categories?
You asked that, and
Yeah,
the
I
answer
don't
is
quite
the
understand.
answer is that that's why I gave the apple red. Do I have apple red here? No, I don't. The reason I gave apple red was because if you say apple, that's clearly a name. If you say red, that's clearly a name. If I train you that when I show you a red apple to say red apple, that's another name. It happens to be a composite name, but it's just another name. You're not telling. You're just saying that's an apple. That's a red, and that's a red apple, or it could have been called a squiggle. It doesn't matter. It's just a name. Whereas if you say apple is red, you're actually saying something. And think of the simulation that in that case you have two. In the return case, you have two existing categories with existing names and existing features that let you pick them out. And you get to the new one by simply saying the new one is just the first and, Boolean and, the second. That's a proposition. That's different from, it's not that the name of the return category is eat Mark. It's not. Although you're right to say that this toy simulation doesn't sort those two out. And you were right to say, how would we sort this out?
Okay.
Well, it's the same problem as with the apes. Yes, that was a good point. Okay, so I'm almost done. So in the same way, no, I'm not. There's in the same way that you got the returnable mushrooms with the edible and the markable ones, you get zebra with horse and stripes, and that gets you, and by using the things that are already in your kernel, it gets you out of the Chinese dictionary problem. We've already done this. We also did physiological studies on this, comparing what happens in the brain when you get a new category by induction, which is the trial and error old way, and by instruction, the new verbal combinatory way, propositional way. And both, in performance, actually, I skipped something in the prior slide. No, I didn't. Okay. I don't know what this is going to do in my presentation, but both the induction subjects and the instruction subjects, of course, learn. There's a difference in their pattern of learning. I'm not going to trouble you with it, but the most important thing is that they all get the late positivity. That's a sign that you've learned the category. Whether you get it by induction or by instruction, the late positivity is there. There's some differences in features. I'm not going to trouble you with that either. I won't trouble you with that either. But I want to leave you with some challenges that are not answered here. Clearly, something happens when we move from the kind of auto-associative iconic learning that you can get with pantomime and with pointing to this new stuff where you say, the returnable stuff is the markable and the edible stuff. In the toy simulation, it's no more realistic than our toy dictionary. It's just a sort of a proof of principle. But what was it in our original environment? What were the circumstances that made it available to our ancestors and that demonstrated its power, because its power is unquestionable? That's still a matter of speculation. Some people like to say that it was just a series of proto-languages, and the proto-languages got simpler and simpler and simpler. But as I said, I think I told you, I don't believe in proto-languages. If it's something in a language at all, if it has the proposition, then it can say anything and everything. There's no such, yeah.
Why do we care exactly why and how language first came about? What does it tell us?
Well, I mean, remember Pinker and Bloom's paper, there is something special about our species because of this. It's very powerful. And it would be nice to know how and why it began, wouldn't it? And this is a hypothesis about it. It says that somehow we discovered that it was a powerful new... You can see how you could get from gestures to category naming, arbitrary names, but what use would it be to name categories if you couldn't talk about anything? So we had to discover, having done a lot of communicative gesturing, that these arbitrary category names could be used to combine to define and describe new categories. That's the hypothesis. Yeah.
Doesn't whether you call it a proto-language or you call it another kind of communication, doesn't there have to be something that was between
Yeah, no, the whole point is that it's no use talking about a series of proto-languages because the stuff that varies as you move to lesser and lesser proto-languages is trivial. The non-trivial step is the step from pantomime and pointing to propositions. And that's an all or none step. Either you're doing it or you're not. Either you're giving a name or you're just giving or you're giving a description. Right? A name is just an arbitrary association between a gesture or a sound and an object or a kind. We have categories. The issue isn't categories. The issue isn't that names are connected with categories. The issue is when do we step over the line and start describing? Because once we describing, we're in business. We're practically at this seminar, right, from the Paleolithic era.
But regardless, there has to have been a proto-language, no?
What is a proto-language? The word proto-language was first invented for things like Proto-Indo-European. It's a language that preceded Indo-European, any of the Indo-European languages. It's reconstructed. Nobody talks it anymore. And then there's a proto-proto and a proto-proto. That's all languages. There's nothing interesting there. It starts to get interesting when you get from zero to language. This is just to remind you that in a symbol system, it's syntax that determines whether an expression is well formed, and it's also syntax, computation, that determines whether it's true. 0 plus minus equals 1 is ill-formed. 0 plus 1 equals 1 is well-formed and true. 0 plus 1 equals 2 is well-formed and false. And in a symbol system, that's all just ungrounded symbol manipulations. Whereas in the case of real dictionary, it's connected, thanks to our T3 powers, to the things that the words refer to. Yeah?
Yeah, how is true ungrounded?
Shrew?
True.
Oh, true.
When you have 1 plus 1 is 2, and so we know that I get syntactically, well, that's well grounded. Well, that's well put, but I don't understand how we can know that's true without 1 having a meaning.
Because the rules tell you. There are two different, it's a legitimate question. In a formal symbol system, there are actually two syntactic rules, two sets of syntactic rules. One determines which expressions are well formed and within the system and which ones aren't. And then there's another one that determines which of the well-formed expressions are true. And true just means obeying these rules. The meaning of true isn't part of the system. It just says, follow these rules and you'll get these. Don't follow these rules and you'll get those. So they're all syntactic. It's just squiggles and squaggles. So anyway, I'm done. This is the categories that you get from being able to combine them Booleanly. Intersections. We were talking about vanishing intersections. Well, intersections are defined in language. And in the end, when you get zebra equals horse plus stripes, this is sort of redundant with what I said before. It's not as long as it seemed. I'm done. Next week we'll be talking about Chomsky and